Okay. Right. Turns out I had kept myself on mute all this time, so that part of the recording is not really useful. Okay. So hopefully all of you can see the front part of the instrument. This is the 4-port network analyzer, which means it can compute scattering matrix of up to 4 sources. Sorry, 4-port networks, which is again rare. I don't know if some of you can see that the port number 1 has an orange light lit on it. That basically tells you that this is the port through which the power is coming out. Now that of course will depend on what is the measurement we have actually set on this. So one of the standard things you do is you go to the stimulus menu, which is now you can see it on the right of the screen there. And this gives you the start frequency, the stop frequency, or equivalently as a center and span. Okay, so currently this is set to its maximum range. This particular instrument has the ability to measure from 300 kilohertz up to 20 gigahertz. That's the range of this instrument. You set the sweep to whatever range you are interested in studying. So some devices might not work outside a certain range, so you can restrict it. But it's just a question of whether it's going to display the data on the screen or not. And it will sweep the frequency over that range with some parameters which are given in this sweep setup. So the important ones to look at are these points. So that actually tells you the number of points this entire range is split into. So it's not a continuous sweep in that sense. Every frequency point is independent. So it's sort of a digital type of step. And there are ways you can construct the sweep. Usually linear frequency is the most common one. So that's linear interpolation. But you can also have log frequency. You can have something called segment, where you have multiple different frequency ranges sort of set together. And then you can have something called a power sweep, where instead of changing the frequency, you keep the frequency fixed and you sweep the power. Okay, so these are used for nonlinear measurements in some cases, but most standard you will use linear frequency sweep. You set up the time here. The lower parts are for more advanced functions. We will not worry about that. Then there is a setting called sweep time, which is currently set to auto. And this is related to the amount of time it spends at each frequency. And that is connected to this quantity called IF bandwidth. So during this class, I'm going to be introducing lots of new terms, but these are all very standard terms you need to understand in order to be able to use an instrument like this and interpret what the results mean. So what exactly is happening? You can think of this network analysis as an independent set of measurements for each frequency. So then you ask the question, well, how long is it going to sit at that frequency and measure? That is given not in terms of a time, but as a bandwidth, basically sort of inverse time. Okay. So 1 kilohertz here basically tells you that it's going to be approximately sitting at that point for about a millisecond. It's not exactly the same. There are some overheads involved and how the bandwidth is defined. But alternatively, you can also think of this as saying that if I'm measuring the data at 1 gigahertz, what I'm really measuring is in a window of 1 kilohertz centered around 1 gigahertz. Okay. That's what this means. So the larger the IF bandwidth, the smaller the time it's going to spend at each point, and the faster the sweep would be, and vice versa. So if I now go back to the sweep setup.
What does IF stand for?
IF stands for intermediate frequency. I'll just elaborate on that in just a second. So if you go to sweep time, and if I click here, it actually displays the current sweep time. It's 1.4863 seconds. Okay. So let me go to this IF bandwidth and set it to 2 2 kilohertz and come back to the sweep setup time. So you see that it has roughly become half of that bandwidth. Now you might say, I want the fastest measurement possible, so I should make this IF bandwidth as large as possible and make my sweep time as small as possible. Yes, but the price you also pay here, in some sense, that time it's dating is also the averaging time it integrates for that amount of time over that at that frequency of measurement. Which means that if you are going to spend less time, you're going to have more noise in your signal. So your scattering matrix parameters will look noisier, so it will have some fluctuations. We'll see that in just a second. So that's what you have to decide. This is exactly equivalent to essentially saying that I'm averaging for longer at the same point to improve my signal to noise ratio. Now, in addition to the IF bandwidth, because that sets what is happening in one sweep, so it's basically going to go to one frequency, wait for some time, integrate, calculate the value, then move on to the next step, and move on to the next step, so on and so forth. But sometimes, even the largest or the slowest sweep you can do might not be enough to get enough signal to noise ratio, or you might have other reasons for wanting to sweep fast. It depends on your experimental requirements. But then you can repeat that sweep over and over again and average that like that. So it's like instead of sitting here and averaging, then moving to the next point, you can sweep, come back and sweep again, and then the two points at the same frequency can be averaged. And that is set here by this averaging factor in the averaging menu. And you have to, for that, you have to turn the averaging on here. Okay. So this would average 16 sweeps and display. Usually it does it incrementally, so you see that the averaging is happening. And then once it reaches 16, it will throw the first one out of the memory and add the latest one into the memory. That's a standard way of first in, first out kind of protocol. Okay. Now coming to the IF, why is it called IF bandwidth? So in all microwave analysis which involve changes of frequency, usually we will have three terminologies which are used: local oscillator, RF frequency or radio frequency, and IF frequency, which means intermediate frequency. Okay, it's just a fancy name for saying low bandwidth. And usually it's because you will take two high frequency signals, which are slightly different, and create a difference frequency, which is a smaller number, and that is this intermediate frequency. So if you have remembered in that diagram, there are all these cross inside a circle. Those are actually the frequency converting devices, the ones which release. So the bandwidth here refers to the mixed down signal, because that is actually what is giving you the scattering wave amplitude. So it's a low frequency amplitude of that mixed down signal, so it's called IF. Such a nomenclature. Okay.
Can you repeat that by doing the averaging releases? Suppose I am at a point taking 16 seconds for one sweep, and if I take each sweep for 1 second, 16 seconds, how does that work?
Because your the signal is coherent, it comes back always measure the same phase, whereas the noise is random. So this is just like, so it's no different than sitting at the same point and measuring for longer. It's just you're doing it in installments. You took a little bit of data, you came back and took another data, and then you average it. So this is, by the way, this is just signal processing in general. This is true for anything. Right? If you have a signal which is always going to come back in the same phase, because here remember the what you are measuring is phase sensitive, right? The things going to extract with reference to the original signal you are stored in. So every time it measures the same quantity, the signal part is going to have the same phase. So when you add it, it will add coherently. So basically, it's like saying the first time, let's say the noise was S, sorry, the signal amplitude was S1, the noise amplitude was N1. The next time, the signal amplitude is going to be S2. But S1 and S2 are actually coherent, so they will add together to give you a larger signal. But the noise is incoherent, so it will go down as a factor of root n. So you get the standard, Cessna improvement of root n. So this is the standard signal process. Okay. There are some additional things you can do to make the trace look nice, like smoothing aperture. That's just adding another filter or equivalently clumping 4-5 frequency points into one point and calling that one number, just called smoothing. But again, these are not super important. Okay. So coming back to the standard settings, so the frequency sweep, then you set the sweep setup, the number of points, you set your IF bandwidth, and any averaging you would like. Right now, let me turn this averaging off and keep the IF bandwidth at 2 kilohertz. So then finally, you have to choose what is it you're measuring. Okay. And for that, so it lists all the possible scattering parameters which this instrument can measure because it has 4 ports. So it's giving you all the combinations from S11 to S42. Okay. So currently it's set at S21, which means it's the measuring the scattering parameter going into port 2 from port 1. So remember that the first index is the destination port, and the second index is the source port. That's the convention that is used. And because the source port is 1, that's why the yellow light here is currently on port 1. If I change this to S12, then the source light shifts to this here. Now, this is basically a cost-saving measure. They could have had separate sources for each of the ports, and some more expensive vector network analyzers do have more than one port, like one source, because it means that in this kind of an instrument, if you have a device which may be, if it's not passive, the passive instrument doesn't really matter. You can only put power in one port at a time. You cannot put power in multiple ports, and that's just chosen by which measurement you choose. There are some instruments where you can have multiple power sources also kept inside. So in that diagram also there was this switch which was showing whether it's sending power to port 1 or port 2. So here also this one only has one microwave source, a tunable microwave source which covers the entire 300 kilohertz 20 gigahertz. And those are expensive to some extent. So they usually only have one source in these kind of instruments. Okay. So let's start with the simplest device we know. So I've shifted back to S21, and this is your simple transmission line. This is a coaxial cable with SMA connectors, which is the standard for all of these instruments. Though actually the ports on this VNA are of a different type. I'll discuss that later. We have put an adapter on it to make it SMA compatible. And this is a flexible one. So I'm going to connect it between port 1 and 2. A practical tip here is you have to make sure you hold the connector loose and align it so that the threads rotate easily. You should be able to rotate it with your finger. If it's not rotating, then there is a problem. Never force it, because there's a tool here to tighten, and this should be only used to tighten right at the end. It should be able to move freely by hand. Now, in some very special cases, if you're working inside a very limited space and the cable is rigid, you might not be able to get it, and then you can use it, but you have to use with judgment, which comes from experience. The reason is that what's happening is really that it's going from a coaxial connector which has a like a hole in the center, and there's a pin on the other side, and that has to go carefully into that hole. If your connectors are misaligned, then you can force it and you might damage the pin, or you could damage the threads. So you have to be very careful. Hand tighten all the way. And then this one is a special type of a wrench called a torque wrench. So if I press it too hard, it basically bends and makes a sound. Okay, and it's tuned to some force, which you should buy when you buy this particular thing. So you tighten it. The moment it makes that sound, you stop. So that way you always tighten to the right force every time. That's important, because these connectors, again, if they don't tighten properly, then they can leak microwaves from that joint, and then it won't work as well as possible. So it's important to do this. Sometimes you might see that your handwriting is good enough and you don't see a difference. So it's always good to use a torque wrench and know how to use it properly. So I've connected it now, and the thing is gone all the way to the top because the scale of the screen is not set. So that is the next setting you should know about. You go to scale here. It tells you how the screen is divided. So 2 dBs per division. So everything here right now, I guess I missed one important thing, which is the format. Okay, what is it going to display? Since S parameters are complex number, there are actually different ways of plotting it. Right now, it's plotting the logarithm of the magnitude. It is basically 10 log base 10 ratio of powers, or 20 log base 10 ratio of voltages. That's the definition. And this is the most standard way one looks at in log units. I'll come to the other ones in just a second. Then in the scale, you just set, so it's 2 dB per division. So that tells you that each time you go down a box here, and you can see, and the reference value basically is like the offset on the screen. And that is set to -10. And the reference position also is given, which is the 5th division. So it's this point here. So this point is here 1, 2, 3, 4, 5th division. And the value is -10 dB. And the scale is 2 dB per division. So with these, you can position the thing anywhere. So we know that this is just a simple transmission line, so it should have a transmission of close to unity. Okay. So in log units, that's 0 dB. So let's set the reference value to actually 0 dB. And your signal now looks as expected, right? But the other 2 ports in this configuration, you don't have to come because this is the measuring instrument, not the network you are measuring. So nothing is happening on those ports right now. Either power is going in, even if this, the detectors are also inside are switching between these ports. So the termination part refers to the network you are measuring, not the instrument. So here, if you don't terminate those ports, ideally speaking, nothing should happen. So here you can see it's not obviously 100% perfect in the sense that it's not giving me 0 dB. Let's zoom in a little bit. Okay. So one intuition you have to develop is to look at something like this and realize whether it is something is wrong or not. This is perfectly fine, but if someone quickly looks at this, they say, "Oh, this is a horrible cable transmission is going on over this." But it's a tiny fluctuation. And usually at higher frequencies, it's going to always happen, both due to the fact that at higher frequencies, all your devices, the tolerances are not very precise. And plus the measurement also becomes usually harder and less accurate at higher frequencies. But here now you can see the speed. The reason it's fluctuating is that each time it's going across the sweep, it's measuring a slightly different number. Now, it shouldn't really fluctuate at all, but again, look at the fluctuation over so I'm talking about the slow movement sweep by sweep over the range of fluctuation here. So that's sort of the accuracy or the stability with which you can measure. If I now do something funny to this cable, you can probably make this worse, but this cable looks quite decent. But otherwise, a flexible cable like this can actually have some effect when you turn it. Maybe in the phase, we will see in just a second. Now, if the question is, are these fluctuations here, is this a frequency response or is it noise?
So what is the x-axis? Frequency?
Yeah, x-axis is almost always frequency. So we can see it here, 300 kilohertz to 20 gigahertz. So it's a frequency response, right? Because it's stable. There is some overall motion like this, but the change with frequency is repeatable over and over again. So this is something to do either with the cable, the connectors, or the network analyzer itself. Okay. So if I now make this IF bandwidth very large. I think this one. So now you see noise. Right? On top of the pattern doesn't have a fine line now, it has this overall noise on top of it. This is because I'm not spending enough time at each point measuring for long enough. Okay, so whatever the receiver is there, it has a certain amount of noise. So you have reduced the time. So let me see what's the highest. So I have not gone to 1.5 megahertz I have bandwidth. And now you see that on this scale, the noise has become huge. Okay. One important thing to notice is that something weird is happening here, right? This looks much less noisier compared to this, and it's roughly halfway through the thing. This is a feature of the instrument. At higher frequencies, usually what happens is that it's very difficult to design an active circuit which works over such a large range of frequencies, a single circuit. So what it will usually have are multiple amplifiers, multiple receivers, which are shifted automatically when the frequency changes, and they will have different noise properties. So what it's saying is that the receiver noise is much better at lower frequencies, but at high frequencies it's quite bad, and it gets really bad at very high frequencies.
So what is that frequency where the
Sorry?
what is that frequency?
This frequency is, I think for this instrument, let's see. So you can also, there is a menu called marker, which allows you to put like a marker here and read off. So roughly it's around 8.5 gigahertz or so. So you will see when I go to a lower resolution that something strange happens. That there's a receiver chain which just has an offset in Yes, so what you are seeing changing is the sweep changing. So it goes from 300 kilohertz to 20 gigahertz in a time of now 48 milliseconds. And then it's doing the same thing over and over again and just updating the values. Because the result is noisy, each time the noise is different, so you see a different timing here. Okay. But if I now go to averaging and turn on averaging, you now see the effect which I was talking about. So same IF bandwidth reduction can be achieved by averaging in time. So the only difference is in IF, as you reduce the IF bandwidth, it averages at the same point, whereas now it goes and averages like that. It's really just the order in which these things are happening. Yes, so you still see some fluctuations. So what will happen is that when you first, of course, start the averaging. So if I click this averaging restart, so then it starts from 0, but then it will add the first 16 numbers, and then after that, it will remove the first one, add the next one, and so on. So it's called a moving average. So you see the last 16 averages displayed on the screen, and even 16 averages at 40 milliseconds is quite fast on human time scales. So you are able to see this. But if I make the averaging bandwidth now quite small, you will see that it will update now a lot slower. So this is now 1 kilohertz bandwidth, but with an averaging factor of 16. Okay, so now you see the refreshing rate has slowed down significantly because it's going to take 1.48 seconds into 16. So approximately 16 seconds it will take to update this whole.
Very it's it is giving the data of the last 16 thing or the total.
The last 16 traces averages. Yeah, after that it updates it. That's what it is. Yeah. I was also looking at it and said, oh, it's not getting 16 seconds. But what will take 16 seconds is this. If I do average restart, then because the IR bandwidth is already so low that you're not able to see the. Then now it should take about 2 seconds to get to the, from the, like, a really bad noise to the average noise level gets that. And then the update time, you write, it's every sweep time, which is in this case, right now it's 189 milliseconds. Okay. So this is S21 log magnitude. Let me kill the average so that we can see things a lot faster. And we can maybe make the IF band slightly smaller. That's a decent refresh rate. So you go to format, and then you have a whole bunch of other options. So you can also do linear magnitude, in which case it should be 1. Right? So now the scale doesn't work well properly, so we go and this position. So you see that now it's close to 1. And on this scale, you see the fluctuations look relatively very small. It's because in the log scale things get exaggerated as well. You can look at the phase. So it's actually a very short cable, but you can now see that the phase goes from 0 degrees to something like 1 degree or 1.5 degrees at 20 degrees. So this is what happens as you change frequency. Why is that? The amount of time it takes to travel from one pole to the other, delta t, is going to tell you is the time difference, and the phase is going to depend on the frequency. So sine omega delta t is actually the phase at one side. Right? That's the, so if something left as sine omega or sine theta here, then when it reaches the other end, it's going to be theta plus omega delta t, but delta t is the time of travel from one end to the other end. That is now plotted as a phase out here. So this cable is, I think, about 9 inches or something. Yeah, no, this is a 12 inch cable. So it's giving you a phase accumulation of about 1 degrees from 0 to 20 gigahertz. You can also plot it as real part. The real part is again basically close to the magnitude, it's about 1. And you can also look at the imaginary part. Because the phase was only going from 0 to 1 degree, the imaginary part is essentially close to 0. This has a small change. You can see the real and imaginary in these polar plots, which sometimes can be useful for visualization. And there's a particular form of polar plot called the Smith chart, which is usually you might have seen some plots like this in POSA. This format is very rarely used. At least we never really look at anything in this format. Back in the day when computers were not available, when you were doing this analysis, the Smith chart was a graphical way to understand things about what's happening. So there are special rules of thumb for what happens when you go to resonance on a Smith chart. You make some art. If you are going from one radii to another radii, what does that mean? So those kind of things you used to have, and POSA actually has a discussion of these things, but almost never do we use now because everything can be calculated. And these are basically now computers. And some of them have fairly sophisticated analysis functions, so you can do that, but these options are available for you. So usually, like in our lab, we use log magnitude, linear magnitude, or real and imaginary parts to understand what's going on. Okay. All right. So this was S121. So now let's look at S11. Let me go to log magnitude. And what should I expect for S11? S11 full transmission. What units am I in? I'm in log units. So in log units, 0 reflection means minus infinity. Of course, nothing is, as I said, nothing is 0 reflection. So here you are seeing a fairly low level out here at low frequencies around minus 30. This means 10 to the minus 3, right, in power. But it gets progressively worse. And of course, there is all this ripples here. And in fact, I'm surprised that it's almost at 1 at 20 gigahertz, which is kind of strange because, sorry, it almost is at 0 dB. Because when we looked at the transmission, it was here. That still looks fairly close to 0 dB. So something is actually not very correct here. Let's check first. Wait. Much better. So this is again a feature which has now become a bug. There was this thing called data map, and that was set to data divided by memory. That basically is a method where you can save one of these S parameters as a function of frequency and put it into memory. And then you can do operations on the current data. So you have these kind of options. You can do data divided by memory, into memory, minus memory, plus memory. Usually the most commonly used one is the data divided by memory because you take some reference curve and you see how much it is increasing. So for example, if I was trying to measure an amplifier or an attenuator, I might connect a cable first and just measure the transmission, and then I'll add the attenuator and say how much does it change. But I don't want to, if this cable has some finite losses, I want to remove it from the analysis. So I just divide it by the reference space, which I have saved. So the way you do that is you go to this into this memory and you say data to memory, which means the current trace goes into the memory, and then you can do any operation. So this thing was set to data divided by memory, which is also why the S21 was looking too perfect. Okay. Now this is much better. I was also a bit surprised at why this was happening. Somebody must have set it like that. So this is a more realistic response for a cable like this. Fairly low attenuation. In fact, this attenuation is also a little on the higher side, but okay, minus 3 dB. My suspicion is that the instrument currently is not optimally calibrated, and I'll actually talk about that a little bit later. And then it slowly increases, the attenuation increases. And that's just because this is a finite conductivity cable. And at higher frequencies, you're going to get more loss, and both due to the dielectric and the metallic response. And then you see this little jump here. This is basically where this receiver is changing. This, I don't know, this machine is quite old now, so maybe this has been like this for many years, but usually when it calibrated well, it should not be doing this. It should have taken into account. But then it goes and you almost reach close to like 16 or 18 dB of loss in this cable, this nice cable is at 20 gigahertz, it's quite lost. It's 20, nearly 20 dB. It's like a factor of 100 in power. So these are things in practice you have to be careful about in an experiment that you have very long cables and at high frequency cables also. So the semi-rigid variety, the ones I had shown, which are the solid core, they will have less loss than these particular type of cables. Now let's look at the S11, which looks a lot better, more visible. Yeah.
Or this is the power, not the voltage.
So this is log of power ratio is what this is. Or, so well, okay, it's 10 log, let me write it down here. So it's 10 log to the base 10 P1 over P2. So whatever P1 and P2, the two ratios are, depending on the measurement you have set. This is the same as 20 log base 10 P1 over P2. That's very simple because P1 is something B1 square and this is V1 square. So then that 2 comes out and gives you 20. So that's what is plotted here. So out here at low frequencies, you are at somewhere around minus 30 and maybe up to minus 20, up to about 8 or 9 gigahertz. This means this is like less than 1% reflection. This is less than 0.01, 0.1% reflection. So what it's basically saying is that most of the power is getting absorbed and going to the other side. So there is very little reflection on port 1. It gets worse here and then somehow settles down here. So this is again a very typical trend that higher frequencies, the reflections will typically get worse. These weird dips you are seeing, again, because of the log scale, this looks very exaggerated. Suddenly it looks like it's a very good cable at this point of time. It is, in practice, there is very little difference between this point and this point. And these happen because of interference. Both sides have reflections. And at certain frequencies, some of those reflections and things can actually cancel each other out and give you a nice destructive interference to give you these dips. And at other points, they actually make it worse. And those are corresponding to these peaks. So when you're looking at S11 data, you should not worry about these very fast changing results. You should just look at the overall trend. And a rule of thumb for any typical cable or connector or something where you're looking for reflection, better than minus 20 dB is considered okay. In some cases, you might want to do better. So this cable is decent up to about 10 gigahertz, not so great after that, even though here it seems to be around, the mean is around minus 20 dB. You can look at it from the other side. So if I go to S22, so let me actually put this to memory, and we can also display the memory trace along with the actual trace. So this, I'm now measuring S22. I'm measuring reflection from the other side, and you see that it's not the same. At low frequencies, it's similar, but at high frequencies, this side seems much worse. Okay. Does this make sense? Like, can it be like this? This is a linear system, right? So it seems to be reflecting more from one side. But here, by the time you come here, it's almost reflecting a good amount of power. There is a possibility that part of it is due to the instrument not being in the most optimal state. But this is actually not completely crazy. Why is that? How can the cable looks nice and symmetric on both sides, but you don't know who made the connector. The factory could have made the two connectors not exactly the same. There could be some difference, maybe there's some little bend there, maybe I didn't tighten the thing. But if it is reflecting badly from one side, you would expect it to show on the other side as well, because this is a just a transmission line. But you saw something which should tell you why this is still acceptable. And with the caveat, I'm saying that these numbers are probably not exactly correct because of the status of the instrument. Why is that? Let me show you transmission once again. Maybe this should give you a hint. I can't hear. This is corresponding to?
Basically, this is S21.
Yeah.
So,
Oh, maybe just hold on one second. Let's just confirm one thing at least. I'm going to put this one to memory now. And this was S21. Let me show you S12. Sorry, just give me one second. It seems to be particularly. Just give me 2 minutes. Unfortunately, this seems to be in quite a bad shape to discuss these subtle points, but let me make it anyway, and then we'll look at other things which are not so critical on this.
so some of that class at 5:30.
Yeah, yeah, yeah. What is the? It's 5, right? So another 15-20 minutes. I'll leave you at by 5:20. Someone just keep remind me when it's 5. It's all wrong, but yet I want to come back to this point that can you have very differing reflections from either of the poles? And I'll answer it also. I'll say yes, but in what condition would something like this still be physical? Remember here, it's going to measure the total reflection, which could happen from anywhere. So S11 means that the other port is terminated with 50 ohms, and it's measuring whatever the power is coming back. Okay. Now the port is terminated with 50 ohms, but we are saying that maybe the connector is bad. So you could have a reflection right at this point, or you could have a reflection right at that point. Let's for the moment assume that the cable itself is. So these are the 2 points of reflection you can have. So the net effect is going to be some interference between the reflected wave which happens at this plane and something which will happen at this plane. And suppose it's complicated because some part will be reflected, some part will be transmitted, and that transmitted part will get reflected again. So you can get some weird things that could give rise to it. Now imagine that one connector is particularly bad than the other one. Now, if this cable was completely perfect, both in terms of not reflecting anything, but also in terms of transmitting everything, then the reflection from the further port, bad connector, will actually still affect your reflection measurement on this port because that power is going to come back. However, if this cable was lossy, which it always is, depends of course on how much loss. Now, right now, I don't even trust that it showed that it had about 18 dB of loss is even correct. Which again, I was surprised when I looked at the number, but I haven't looked at this in such a long time that I guess I've lost my intuition. This cable should have a few dB of loss, it's too short. But if it's lossy, then what's happening is that you can have, let's say this connector is the good connector and this connector is a bad connector, and you're measuring, this is port 1, port 2, and you're measuring reflection from here. So the reflection from this plane is going to be very less. The wave will travel, it could get reflected quite badly out here, but that wave is going to have a round trip through the cable and will get attenuated. If this loss is big enough, then you might not even see the fact that this particular end is badly reflected. Okay, so that's why this, if this was correct, this is still possible, provided you are talking about a system where you have bad reflectors on one side of a network, but the internal transmission is very lossy. So in that case, it's possible. So I will try to fix this instrument tonight, and or we have another one to check with this, because there are many subtle things which will not make any sense if the measurement is all over the place. Okay. So since I have about 10 minutes or so, let me quickly show you some other devices and also understand this issue of terminating the ports. So here is one device I wanted to show you. I actually have two of slightly different types. They look sort of exactly the same. It's a 3-port device. It's one of the most common things you would use. And it's a splitter, a power splitter, which takes in power from, usually this is the input port, and then it equally divides the power on ports 1 and 2. Way of splitting the power into 2. And ideally, it splits it in phase, which means the signal which is coming out of those are also in phase with respect to each other. Of course, if you connect a different length of cable on each of those ports, then that phase is going to be dependent on the. This particular one says it works from 2 to 10 gigahertz. So it actually doesn't work at low frequency, and there's a reason to it, because this uses a particular way of doing this splitter called the Wilkinson divider, which we will study later on. This one carries out the same purpose, but works from DC to about 4.2 gigahertz. In order for a splitter to work at DC, you cannot use the Wilkinson divider one, and it has a consequence. So we will understand this when we look at that in more detail. That this particular one is able to give you the equal power split. So whatever power goes in comes out of these 2 ports, half and half. This particular one gives you 2 equal outputs, but it actually further attenuates the signal. So a factor of 2 in power is approximately 3 dB in power in log units. It's not exactly equal, but close enough. So it's often something you hear that 3 dB power loss means factor of 2. Again, numbers you have to remember. So 3 dB is factor of 2, 6 dB is factor of 4, 10 dB is factor of 10, 20 dB is factor of 100. Okay, so these are these numbers you should sort of get used to. This one gives you 3 dB less power on the port, whereas this one gives you 6 dB on each port. So the total power out is actually not equal to the total power in, because this one has resistive elements inside which absorb the rest of the power, whereas this one does not. I can see. Now again, most real devices, the split will not be exactly equal. It will change its frequency and it will go up and down, but it will be close to this 3 dB value. So let me connect this, and we will actually use 3 ports, and hopefully the numbers will not be too far off, but let's see what it does. So probably maybe in that case, it's best to compare it with the same port. So I will not use 3 ports here. So let's so I've connected port 1 to the input port of this device. By the way, this I'm calling this input in the device. It's actually labeled as S, but this is a passive device. You can use it in reverse as well, and it will. You have to know what it will do if you want to use it properly. I'm going to take one of the split ports and connect it to port 2 with the help of a cable. The cable will add a little bit of loss, but it should be small at low frequencies. So we can sort of look at what happens at low frequencies. And this device says it goes from 2 to 10 gigahertz. So let me start the frequency at around 1 gigahertz and stop it at around 15 gigahertz. And I'm going to measure S21 because I'm looking at power going from here to here. So this is what I'm going to come to. I have to terminate this port in order to make sure that I'm looking at the right property of this device. Why is that? Because otherwise the amplitude is going to come out here. It's going to see an open end. It's going to reflect that and combine with that one and this one in some strange way. Okay. So this is how you should test it if you're only connecting it to 2 ports. If I have connected this to one of the other ports, then it's fine because that is a 50 ohm convention. Okay. Now this unfortunately looks horrible. Let me look at S1. This is probably in a different direction. It's going on. Okay, I think this is so bad that there's no point in looking at it. But let's just look at the reflection from port 1, and you see that it's absorbing most of the power in this region, right? It's between -10 and -20. So it's not supposed to work at 1 gigahertz. So if I take this marker and put it at 2 gigahertz, that's roughly there. So it's, when it's supposed to be working, and then it sort of absorbs the power nicely. Because it's a matched device, it should do that. There should be no reflection of the input ports. But if I remove the 50 ohm termination from one of them, then you see it becomes horrible. Because it's now that power is reflecting back. It will affect both the input side and the corresponding split port. Okay. So maybe just to check that at least the 2 ports are giving you something, even though it's displaying something wrong. Display data to memory, data and memory. Now I'm going to just interchange the cable and the termination on the device itself. At least this works properly, that it shows that both ports, the coupled, whatever power is coming out, is the same, more or less the same, because these two line up on top of each other. The actual value is quite bad. Actually, about -7. I don't know, maybe it's not so bad, but the thing is, it doesn't measure because this is a linear circuit. The S matrix should be reciprocal. So S12 should be equal to S21. So it doesn't matter. So this is another thing you have to remember, that if you have a splitter and you're going in and out, and you terminate one of them, you look at the power going this way and as 3 dB, you look at the power like this, it should also be 3 dB. So it's a linear kind. So this is one of the properties of S matrices. But here the instrument is showing S12 and S21 to be differing by quite a bit, which is actually this wrong. The instrument is not measured. So I'll end with this point. I'll try to fix this or bring a new instrument. Is that these instruments are not guaranteed to be correct by themselves by design. There is actually a very sophisticated calibration procedure which goes on. And some of these other things I brought here, I guess I was over ambitious on how much I would be able to cover in one lecture. But I think I mentioned this. So I'll just show you here and maybe I'll come in front of the camera as well. You see all these small things? These are all called standards. Okay, so there is a standard for an open. This one is a load. So it's a 50 ohm standard. This one is an open standard. And there's a short standard. So in one of the problems, I think it's probably there in the next homework, which I will email you today, you will see how with the help of these standards, you can actually correct the errors in a measurement in this, using this vector network analysis. But that is usually the case where you are trying to get rid of the effect of, say, a cable. See, in this case, I'm not able to connect the instrument directly to the port, right? I have to put either a cable or this little SMA adapter. So what does it mean? What is S1 and where? So usually the instrument has a reference plane with respect to which these scattering parameters are measured. So if you connect something to it, if it's a pure transmission line, lossless, then it just gives you a little phase change, and potentially one can ignore that. But if it is a real thing like a bunch of cables, and you are only able to connect your device at the end, you would ideally like to not worry about what this guy is doing. So in particular, obviously you cannot have a very lossy cable, because if you put a very lossy cable, as we were just discussing, what is happening at the other end stops to have any meaning, because you do not see it here at all. But for low loss cables, and maybe with some frequency dependence, you can actually do a set of standard measurements. And what does that standard measurement mean? It's by using these standards whose reflection coefficients are stored inside the machine. So you enter a model number for that particular thing. And open ideally should give you a reflection coefficient of +1 at all frequencies, but there is no such thing in reality. So it will be close to +1. But it will be a measured quantity and you feed that into the system. Similarly, the short will be close to -1 and the load is the 50 ohm, the matched load will be close to 0 reflection coefficient. But you know those numbers, and if you know that, then by doing measuring the scattering parameters for these idealized loads, you can back calculate the S matrix of the middle part and remove it from the calculation. And this is actually what the calibration procedure is. So there is a menu here. So right now it says correction off because there is no such correction being done, but there are methods here, and it also has this thing called calcate, and it gives a number there. So that number usually has to match the number which is written on this box. So it's actually not the same one. This one is 85052D. That way it knows which data, and usually earlier days it used to come with a disk and you can even upload the data onto this. So you have to do this calibration. There are more sophisticated automated calibrations as well, because here what you have to do is that you basically say connect the open, press this button, connect the short, press this button. But you can also have a fully automated one. So this one is USB powered, so you connect it to the vector network analyzer, connect 2 of the ports with the cables you are going to try to calibrate out, put it here and just press one button, and it basically, it doesn't work exactly the same way in the sense that it doesn't go to open, short and load things, but it uses some other known standards. And that allows it to remove the effect of any cables involved. So something seriously is wrong, either that the calibration has to be done and hasn't been done in a long time, or there is a serious problem with the receivers. The reason nobody seems to have bothered with this is that almost for like 90% of our measurements, we do ratiometric data. So you could be off by a certain factor, but both measurements will be off by the same factor. You take a ratio and you're good to go with that. So I guess nobody has bothered this, and I haven't checked it in a long time, I guess. So that's why the absolute numbers seem to be a little bit off. Now, this actually doesn't look so bad. It's giving me minus 7 dB when it should be close to minus 3 dB, but it's never going to be perfectly 3 dB because there is some loss in the instrument, in the box itself. So it should be slightly lower than 3 dB, but it seems worse. And the bigger problem is the other one, which is very close to 0 dB. In fact, for the cable, it was showing me greater than 0 dB, which is not possible. So that means more power is coming in than what you're putting into the system. So there's something wrong with that. So we'll fix that and we'll continue with this tomorrow at 11:15. Okay, I'll stop it.